Well, hi everybody. It's Mr. Eckstrom again, and I'm here to talk to you about some things to help you get started with physics. Physics basics, we're going to call them. Some tools. I'm going to teach you some strategies that we kind of use to solve problems and things in general. There'll be a lot more tools to come as the semester goes on, and some general ideas that physicists talk about, or ways that physicists talk about problems. The people that you see on the screen here are two of the most famous physicists ever. Uh, we're going to see if you know at the end, and I'll give you the answers who they are. First thing we're going to look at in this section is about measuring. Measurement is important in all sciences, and physics certainly is no exception. We measure a lot of different things. We'll talk about some of the units that we use and how important measurement is. First thing we want to get behind us in terms of measurement is length. Length is defined as the distance between 2 points. So anywhere in space, if you have one point and you have another point, that's sort of space that connects those 2 points. Well, that's what we call length. In the English system, the system that we use here in the United States, we have a variety of somewhat confusing, not very well connected units for length. One of them is the inch. That's our smallest unit. The inch is roughly the thickness of a man's thumb. That's kind of a rule of thumb, I guess you could go by. A foot is another unit of length, foot. The foot used to be the length of the king's foot. So if you were buying things, you got a better deal. If you had a large king than you had a small king. There are 12 inches in a foot. 12 isn't an easy number to always work with mathematically compared with something that's more related to our digits or 10. And then, of course, there's the yard. Everybody that lives in the United States knows that 3 feet are a yard, but that's not so common in the rest of the world. And also, we have the mile if you want something that's even bigger. The relationship between yards and miles and feet and miles and inches and miles, they're not all based on the same unitary system, and that makes it inconvenient. So most scientists are going to stick with the SI system for length and for all measurements, really. SI stands for International System in French, and the standard unit of length in the SI system is the meter. Meter is abbreviated with a small m. Meter is a little bit longer than a yard, which we're familiar with in our system. Um, and in fact, we measure it with a meter stick, but the real distance that is defined by a length is how far light goes in 1,299,792,458th of a second. If you're measuring things really precisely, that might be important. For us, a meter stick or a smaller version of a meter stick might be good enough for all our purposes. Here are some relatively common and some not so common objects in the metric or the SI system. Here's a human being. Human being is on the order of about a meter. It makes sense that our base measurement unit would be about something in our scale. So a human being, full-grown man would be about 2 meters tall, like it shows on that picture. Here's the Earth. Here's a picture of the Earth. The radius of the Earth, from the center of the Earth out to its outside edge, is roughly 1,000,000 meters, on the order of 10 to the 6 meters. That gives you some scale there. This is our whole solar system. If you measure from the center of the sun out to us, we're the third planet out, that distance there, well, that's Earth's orbit. That's about 10 to the 11th meters. So that's 5 orders of magnitude, or 100,000 times bigger than the radius of the Earth. A light year, the distance that it takes, that light can cover in 1 year's time. A light year is about 10 to the 15th. So again, that's 100,000 times bigger than the radius of the Earth orbit. So much larger distance. You start scaling down. Here's a sugar cube. I have some sugar cubes here. The length of a sugar cube, or the length of an edge of the sugar cube, that's about a tenth of a meter, or I'm sorry, 1/100th of a meter. We call that a centimeter, and that's another common unit in the SI system that's used. It's about 10, 1/100th is about 10 to the minus 2 meters. Here we have a small single-celled organism, a paramecium of some kind, or an amoeba, I don't know. The length of this thing, the rough scale that you would measure this would be about 10 to the minus fifth. 10 to the minus fifth. 10 to the minus fifth would be 1/100,000th of a meter. So that's getting down to a fairly small measurement. And then here's something even smaller yet. This is a little picture that's supposed to represent an atom. Atoms, if we could measure them, they are roughly an angstrom across. An angstrom is a shorthand term for 10 to the negative 10th meters. So that's 1 10/1000th of a meter. So that's very, very small. But everything is based on the number 10, which makes it very convenient. You just scale meters up, scale meters down by factors of 10 for measuring larger or smaller things. So we can use these prefixes. There's this whole array of prefixes. Some of them are much less common than others. These are 3 that are commonly used for scaling things up. Kilo, the prefix kilo, which is abbreviated with K, means 1,000 of something. So a kilometer, or we say a kilometer, is 1,000 meters. So that's a for example. 1,000 meters equals 1 km, or 1 kilometer. Mega, which is abbreviated with a capital M, that means a million of something, or 10 to the 6th. So we could say a megameter if we were trying to measure a very long distance, like in astronomy. We're familiar with mega from computer terminology, as we are with giga, which is abbreviated with a capital G, and giga means a billion of something, or 10 to the 9th. So there are megabytes and gigabytes and megahertz, which is a frequency term that we hear thrown around in everyday language. Scientists use them for scaling units up all the time. Here are some prefixes that scale down the meter and other SI units. Centi, that's 1/100th of something, or 10 to the negative 2. So if you take a meter, that distance that's about a yard, and divide it into 100 pieces, each one of those would be what we call 1 centimeter, 1/100th of a meter. Milli, which is abbreviated small m. Milli sounds like it's starting out to be a million, but it really isn't. That means 1,000, 1/1000th, or 10 to the negative 3rd. So the little teeny tiny marks, like on this picture that we have here, the smallest marks in a yardstick, those are millimeters, 1/1000th of a meter. If you need to measure something even smaller than that, we use the prefix micro, a micrometer. The abbreviation is not an English letter, it's a Greek letter. Mu is how you say that. Mu. And that is a millionth of a meter. So 1/10 to the 6th, or 10 to the negative 6th meters is a micrometer. And if you're measuring something that are very, very small, some objects that are really little, we could use the prefix nano. Nano is abbreviated by a small n, and this is a billionth, 1/10 to the 9th, 1/1,000,000,000, or 10 to the negative 9th. Very small objects are measured in nanometers. There's a whole area of science and technology now called nanotechnology that is involved with creating, and manipulating objects that are on this scale. It's called nanotechnology. You'll probably hear of it again in your future. We can go back and forth between the English system that we use a lot and the metric system, or the SI system that scientists use very commonly, with one conversion factor. This is the only one that I can ever remember, and it is that 1 inch is 2.54 centimeters. That's really all you need to know. But with a few other facts about how the metric system works and things you already know about how the English system works, you can convert back and forth between the SI system and the English system with using just this single factoid here. very powerful in a tool called dimensional analysis that you'll learn about later. Another thing that we have to measure is mass. Mass is sort of like weight, but not exactly. It's related to weight. But more precisely, a physicist would define it this way. It measures the resistance to change in motion. So any object that doesn't want to change its motion unless you have to force it, well, that's an object that has mass. All matter has mass. So everything that you think about has mass. The English unit of mass is named after this property of matter of sluggishness, and it's called the slug. The English unit of mass is a slug. A slug weighs about roughly 32.2 pounds. 32.2 pounds is a slug. Nobody knows much about slugs. We know a lot about pounds. Pounds is actually force or weight, but mass will be measured in the slug. In the SI system, we think of mass as a kilogram. That prefix kilo means 1,000 of a smaller unit called a gram. But the standard is this thing that we see in a picture of right here. It's called the IPK. That stands for International Prototype Kilogram. It's stored in a temperature and humidity controlled vault in France. And every kilogram, or everything that's related to a kilogram, all masses that we measure on Earth, if they're going to be precise, have to be traceable back to this guy right here. That's the target. And everything's related to that. Here are some objects or collections of objects that we can give a rough scale for mass. This is a picture that I'm showing of a huge nebula. I'm using that to represent the whole known universe. This is not a picture of the whole known universe. There are no such pictures. But if you could weigh the entire known universe, scientists estimate fairly closely that that would be 10 to the 52 kilograms. Right here we've got the Milky Way galaxy, the one that our planet lives in. It's just a small part of the whole universe. This whole collection of matter, which includes a whole bunch of stars, a massive number of stars, is estimated to weigh 10 to the 41 kilograms. Here's the sun, our big star, one single star. If you could measure all the mass in the sun, this would come out to about 10 to the 30th kilograms. Here's a human being. This person would be on the order of about 10 to the 1 kilograms. We would probably measure in tens of kilograms. You know, if a person weighed 220 pounds, that'd be a 100-kilogram person. Here's a mosquito, pretty small object. Mosquito would be 10 to the negative 5th kilograms, so that'd be about a 10,000th of a kilogram, much smaller. Here's that same single-celled organism that we saw with length. This would be about 10 to the negative 15th kilograms. And here's the atom. If this were a hydrogen atom, its mass would be on the order of 10 to the negative 27th kilograms. So very, very small indeed in terms of mass. A mass conversion that will be very common, you'll use this a lot probably in physics, is not actually a conversion from mass to mass, but it's a conversion of mass, kilograms, 1 kilogram to force that's used much more commonly in the U.S. 1 kilogram is 2.20 pounds. My script here is not very good. That's supposed to mean pounds. 2.20 pounds is a kilogram.